Dear ladies and gentlemen, hello colleagues. I am glad to present to your attention a paper with the following subject: effect of hot rolling parameters and chemical composition on the structural state and mechanical properties of low-carbon microalloyed steels. High-strength low-alloyed steels are widely used in the manufacture of vehicle, pipelines, building, engineering structures, and other objects of various properties. This is due to a good combination of surface properties: strength, plasticity, permeability, fatigue, and corrosion resistance, as well as technological properties. The unique set of properties of these steels is ensured by the formation of a finely depressed homogeneous ferrite structure and a system nanosized phase precipitates containing microalloy elements. Manufacturers of modern automotive steel sheets service in use the most cost-effective alloy variants. Therefore, relevant studies are currently being actively conducted. Special focus is given to searches for patterns of influence of chemical composition and parameters of hot rolling of metal on the formation of microstructure and the system of nanosized phase precipitates of different types and ultimately the obtained mechanical properties. This work is one of such studies. Low-carbon steels which different combinations of macroalloy elements from the general vanadium, niobium, titanium, molybdenum system produced under laboratory conditions were studied. The steels were smelted in vacuum induction furnace with magnesite crucible. The chemical composition of the investigated steels are presented in the table. These steel ingots of all compositions were heated to 1250 degrees centigrade and rolled on a reservable rolling mill into strips of 3 millimeters thick with a rolling end temperature of 900 degrees centigrade. After the rolling ends, the strip was cooled in an air stream with a cooling rate of 10 till 15 degrees centigrade per second to 650 degrees. When the strip was placed in a furnace heated to 650 degrees, kept for 30 minutes, followed by cooling with the furnace, simultaneing the cooling of a roll. This slide shows the results of mechanical properties determination. As can be seen, the strange characteristics of the rolled samples vary over a wide range, rising with increasing in vanadium, niobium, and titanium concentrations, and when molybdenum is present in the steel composition. The values of relative elongation have close values in the absence of a definite correlation with the strange characteristics. To clarify the noted features of the behavior of mechanical properties, a study was carried out of structural state characteristics and present phase precipitated in rolled steels. By means of scanning electron microscopy, it was found that all studied samples have a close ferrite macrostructure. A typical view is shown on this slide. To establish the mechanism or the influence of chemical composition on the structure formation and the properties of these steels under investigation, a detailed study of their structural state and the carbides and carbonitride precipitates present was made by transmission electron microscopy. It was found that the metal matrix of rolled samples from all steels consists of ferrite of two morphological types, block and polygonal. This slide shows a typical view of block ferrite. It's characterized by a dislocation density from medium to high. The shape of the block is closed exoacid. The elongated shape of the blocks in rolled steels number 1 to 3 was not found. In samples of steels containing molybdenum, which is exception of steel number 6, it was rarely observed. In steel number 6, the shape of the ferrite block is predominantly elongated and rarely closed to exhausted. Polygonal ferrite has a dislocation density varying from low to medium, grain size as a rule up to 10 till 15 nanometers. In some cases, steels number 2, 3, 5, there are separate grains larger than 15 nanometers. In all steels, except number 2 and 3, the volume fraction of block ferrite is predominant. In rolled steel number 1, rarely located regions of quasi-polygonal ferrite are also detected. This is the image of the right. All the steels, with the exception number 4, 6, 8, a small amount of cementite was detected. It was the form of separate precipitates along the boundaries of grains with size up to several micrometers. Detected nano-sized carbonitride precipitates belong to two-dimensional types. The first type included elongated precipitates formed in austenite up to 10, 15 nanometers in length and not more than 3-4 nanometers in width. In the case of steels 1 to 3, they were searched out in approximately 15 till 20% of ferrite grains, which have a favorable orientation of their detection. Herewith, in close grain in which they are present, their number is usually small. In the case of steel number 4, 6, and 7, and 8, these precipitates are significantly more representative and are found out in about 50 till 75% of ferrite grains. The minimum amount was observed in steel number 5. Another size group consists of nano-sized precipitates of interface type which are systematically present both in grains in which precipitates formed in austenite are presented in the grains in which they are absent. Except of steel number 5, apparently interface precipitates are localized in almost all ferrite grains. The size of precipitates observed in most sections is up to 3-4 nanometers. Regions where interface precipitates are larger, up to 5-6 nanometers are rarely found. No precipitations formed in ferrite were detected. The obtained results of analysis of carbide precipitates amounts can be explained using thermodynamic calculation of the temperature dependencies of the equilibrium phase composition of studied steels. They are presented in this slide for steels 2 and 4, which are characterized by minimum and maximum strength properties respectively. The fraction of titanium-based complex carbide in austenite and ferrite in steel number 4 is higher. This is consistent with obtained results. In addition, formation of this carbide in steel number 4 occurs at a higher temperature. Therefore, for this steel, one should expect a greater number of precipitates formed in austenite, which is observed extremely. The conditions of the formation of cementite, complex iron carbide, and molybdenum carbide occur at temperatures below 700 degrees centigrade. As a result of this diffusion inhibition and the composition of significant amount of carbon for the complex titanium-based carbide precipitation, the formation of these carbides is almost completely suppressed. Similar high strange waters are found in steels number 1, 6, 7, 8. Is 665 till 700 megapascals. Steel number 1 has a thinner grain size, which is due to the high concentration of niobium. Steels number 678 contains molybdenum, have the highest content of interface precipitates up to 3-4 nanometers in size. This is consistent with the known data on the favorable effect of molybdenum on the nucleation of phase precipitates and the inhibition of their growth. The decrease in the vanadium concentration in steel number 8 compared to steel number 6 is compensated by an increase in the titanium concentration. The ultimate strength values in both cases are 700 megapascals. Steel number 4, with the maximum titanium content and molybdenum microalloy, has the maximum strength values. The steel contains a large number of interface precipitates up to 2-4 nanometers in size. This confirms the importance of the presence of molybdenum in the steel. Increasing the titanium content in steel number 3 without molybdenum resulted in a less significant increase in strength compared to steel number 2 than in the case of steel number 4. On the other hand, the amount of carbide precipitated formed is directly related to the titanium concentration in the solid solution. Therefore, even with the presence of molybdenum in the composition, with a low titanium content in steel, the possibility of forming a significantly large number precipitated and obtaining high strength volleys is not ensured. This is evidenced by the relatively low values of the yield strength and strength limits of rolled steel number 5. It should be noted that titanium and vanadium have the highest propensity to the formation of the most effective interface carbide precipitators. These alloying metals have a small atomic diameter and therefore a greater diffusion mobility, which allows the process to be implemented at higher rates of gamma to alpha phase transformation of steel. Moreover, titanium has a smaller atomic diameter and higher thermodynamic stability, and hence the higher driving force for the formation of carbide precipitators in steel. The noted circumstances correlate well with the obtained results. From the table, it is evident that the rolled products obtained under equivalent condition have a higher strength characteristics with a low titanium content compared to vanadium. The precipitation of niobium in the formation of interface precipitators is significantly limited due to significantly larger size and lower diffusion mobility of atoms. Thus, the study of characteristics of the microstructure, phase precipitators, and mechanical properties of low-carbon hot-rolled ferritic steels, microalloyed with vanadium, niobium, titanium, and molybdenum, separately or together, made it possible to establish the following patterns. Cooling of the studies steels after rolling ends and at low speed of 10 to 15 degrees centigrade per second results in the formation of mainly block ferrite. The shape of the blocks is close to equiescent with the exception of steel with a high content of microalloying components where the blocks have elongated shape. In steel with a low content of microalloy elements, polygonal ferrite predominates. All steels content nano-sized precipitators of two types, those formed in austenite and interface. The interface precipitators are most effective for increasing strength. Titanium and vanadium are more prone to the formation of them than niobium. The highest strength is found in hot-rolled steel microalloyed with niobium, titanium, and molybdenum, with a significant titanium content of 0.17%. Due to this composition, the steels a large number of interface precipitators up to 2, 4, nanometers in size. The rolled products obtained under equivalent conditions have a higher strength with a low titanium content compared to vanadium. Taking into account the economical indicators, the obtained results indicate the advantages of titanium-based microalloy systems compared to vanadium. Thank you for your attention.